Yes. So proteins, as most people know, are the main machinery of the body. So when a muscle moves, it's a protein that commands it to do it. Digestion is proteins. Enzymes are proteins. So numerous functions in the body are to do with proteins. And when people are not well, it's often to do because a protein is going wrong or doing something wrong. So our main goal of our whole research is to design new medicines, new and improved medicines. And most of these medicines, they target the proteins. Yes, because if you get arthritis, say, it's a protein which is responsible for it, or AIDS, or cancer, or many things. So what we want is to find a way to block the activities of these proteins that are doing us damage. Now, in order to block something, you need to know what it looks like. Yes, because if I want to attack you, I need to know what you look like, otherwise I'll attack him. You're all people, but you're different. You look different, you do different things. And the same with the proteins. They're all proteins, but they do different things, they look different. And in order to know what they look like, we need to crystallize them. And again, coming back, if one goes to the hospital and you do an X-ray, you can only see the bones or the ribs, what is solid. You can't see the proteins because they're in solution. They're in the blood or in the urine. So in order to see them and be able to X-ray, as we do the solid in the body, we need to turn them into solid. And how do we do that? That is what's called to crystallize them, really to turn them into solid. So that's the reason why. And then if we get crystals of them, then we can put them in the X-ray. We can see what they look like, or in scientific terms, their structure. And if we know their structure, we see how they are built and where we can block them. We can see the active site, we can see what goes on. And that's why we need these crystals in order to design the medicines that will interact with them and block them where we want. Okay?
Thank you, answer. And my second question is, so how much information we can know about the protein at the moment?
Well, structural information, one knows all sorts of things about proteins. People do activity studies and so, but that is in solution. The structure of proteins is much less known about it than we would like to. And there's been big all over the world after the sequencing was done, the genome sequencing. The next stage was to crystallize and solve the structures of the proteins, because the genes encode proteins. So that was the next stage. And millions of dollars and pounds, and in all over the world, including China, came what was called structural genomics projects, who tried to solve the structures of hundreds and thousands of proteins. And out of those, only 20% gave the structures. And why? Because the problem was to get crystals. And once you get crystals, you can X-ray. That's then already not a problem, but what you need is the crystals. And this became a big bottleneck worldwide, and that's why we are trying to crystallize. One needs any method, anything to advance this bottleneck and open it up, that we can get structures of all these proteins, that we need to know what they're doing in order to design medicines for them. Yeah?
Great, and that's like my next question. So why crystallization is difficult to achieve?
Of proteins, mostly difficult because proteins are really biological materials, so they're very sensitive. If you take diamonds, or then you put high pressure, or you put small molecules, or these things, crystals for transistors, many things are crystals. You can put high pressure, high temperature, and quite harsh conditions, and that will make them crystallize. But if you do this to proteins, you just spoil them. They'll just go apart. So you need to be very careful and sensitive, and it's got to be biological conditions, and that's difficult because you see, these proteins, they don't want to crystallize. They're in the blood or the urine, they're comfortable. They say, leave us alone. We don't want to. That's not their natural habitat. Like gems and diamonds and things, that's their natural. They want to crystallize. Proteins don't really. We have to persuade them and convince them gently by giving them conditions that they like so that they should be willing to crystallize. That's really what we're trying to do.
Okay, and my next question is, so how do you think this new technology by your research can help to enable the new drugs and the treatment to be developed?
So as I was saying, in order to develop new drugs, to facilitate this whole process, we need the crystals. So if we get, and as I was telling you, the methods to give, if we have good methods to produce crystals, then this whole pipeline will go much smoother and will enhance the success rate. So any method which is good is very important. And this nucleation is, as Milo was saying, the first step of getting a crystal is the conception stage. Nucleation is really like a baby. You know, the first two molecules, if they're okay, you get a good baby. If too many of them, or they don't go so good, heaven forbid, you get handicapped, you get the IVF when there's too many and they fight each other and all die. You want one or two good. So again, this conception stage has got to be very important. And this is what we are doing here. We are handling the very first conception stage, the nucleation, where the first molecules come together. And if they do it well, which they are using our methodology, then the rest takes care of itself. So we're starting really from the very basic, getting that point right, and then that gives us the crystals. And once we have the crystals, we can get the structure. Once we have the structure, we can design the medicine to counterbalance whatever we don't want it to be doing.
Okay, great. And my last question is, what is your future plan on this research? So will you keep on making a new type of universal crystallization solution that can work all types of proteins?
So as Milo was saying, you can't have something which will work on everything. But this is a major step. It's a breakthrough from the point of view, you see, our research is not a one-off. We base the research on previous things. So even this one is based on previous results, whereby we saw that it is important that there should be kind of pores or plots where the protein molecule can go, which is similar in size to them. And we're getting better all the time. Initially, we just did it in pores. Then we did it in pores which attract proteins. Now, with this graphene material, we manage to functionalize in any way that we want. And as Milo says, here the possibilities are much wider. Up till now, we had materials, they were successful, but not enough because they were limited. This is already widening the possibilities. And our future is to widen it as much as possible, and to build on what we found now to make it even more applicable and universal.
How research?
You're talking the research about the whole research, or you're talking about this specific one? Yes. This nanoscale, yes. So this is a breakthrough from the point of view that this is the most versatile nucleant that we've had so far. So this is based on previous results of successes where we have been working on nucleants for 15 years or even more. And gradually we're getting better and better at it, finding things which are more successful. But this one is better than all the previous ones because of the possibility to functionalize this graphene. We can really do almost anything with it. And that will eventually give us hopefully universal. There's no universal for every single protein, but it will give us possibility to crystallize more proteins than ever before with that one. And if we manage to crystallize, it means we'll have crystals. If we have crystals, it means we have structures. And if we have structures, it means that then we know what the protein is doing, what it's looking like, and therefore we can take it to the next phase of drug design.